Okay, so welcome back to the second hour. So we just stopped when we introduced this wedge flow, which was the original idea of Faulkner's can. And actually, the connection now to the wedge flow, and in particular this exponent A and this Hartree parameter, so this the angle. So this connection essentially comes from Hartree. So that's the calculations that he did. And now we're not talking much more about that, but you can show from inviscid flow, from an inviscid flow analysis over this wedge, what you can find is the following, namely that this beta h is the same as 2a plus 1 divided by a plus 1. So that's the relation that Hartree found. So it means that if you have a specific angle, an opening angle here, you know that the velocity that you will have here is following, or the exponent of the velocity is related to this with this relation. And this is something you can derive from inviscid flow. So that means for any given beta h, you can calculate what your a needs to be, and vice versa. So that's the connection why we may be interested in this case. So essentially, what we then get is the boundary layer profile when we have this exponent a. So that's the whole point. But of course, it's not clear that we can actually get a similarity solution. So we now just talk, okay, well, we want to do wedges and so on, but are we really getting a correct solution, or do we actually get a similarity solution? Well, for that, we actually need to go back to the conditions that we also applied when we derived the Blasius solution. Remember, we had this G1, we had this G2, and we had this G3, where we said, well, in order for this to be a similarity solution, we need to make sure that G1, G2, and G3, that they do not depend on x and y. It's only then when we can get similarity solutions. Well, let's now check what we get for this case. Now, when we assume that we have a velocity profile with a specific exponent a. Well, so if you start with G1, well, that's actually the easiest one because that's actually zero in all cases, because essentially it says that the second derivative of this eta with respect to y should be 0. And because we only have one y in here, because we only have one y, this is anyway given. So for that we're fine. G2 is a little bit more complicated. There we have ue divided by nu times it's this second derivative d eta squared dx dy, and then we had d eta dy to the power of 3. Now we can feed in our Faulkner's can ansatz, this eta as a function of y and x. If we do that, we get ue divided by nu, and then we get for the numerator a times c times x to the a minus 1. So I'm just putting in all of these. And in the denominator, we get c times x to the a up to the power of 3. And if I continue here, I will get ue of x times a divided by nu c squared. And here I get 1 divided by x to the 2a plus 1. So that means if I want to have a similarity solution, I need to make sure that this guy is actually independent of x and y. Okay? Now we just need to do the same for G3. G3, the definition was due dx. Actually, this could be normal derivative because ue can only be a function of x. So due dx divided by nu times d eta dy squared. And also this I can now express in terms of my velocity or my eta that I have assumed here. Which will become due dx divided by mu times c squared x to the 2a. So now what I need to make sure is that this and this, these two guys, they need to become independent of x and y. They're only allowed to be functions of eta. Only then we can do a similarity solution. Now, of course, one thing that I directly see is that if I want to have G2 to be independent of x, that means that UE of x divided by x to the 2a plus 1, x needs to disappear. So that means that UE actually needs to be proportional to x to the 2a plus 1. It's only in that way that I can get rid of the x dependence of G2. So, remove x dependence in G2 means directly that UE of x needs to be, or we can now use an equal sign, x to the 2a plus 1. So then just, I may just write it. I mean, the idea here is these three need to be independent of x and y. That's really our job for now. Okay, and if I do that, then I get for G2 the following. It's just a divided by mu times c squared. And now it's independent of x. If I put that in well, maybe I can do that. 2 steps. Now we need to see what G3 becomes. So due dx, which I need here, is of course 2a plus 1 times x to the 2a. And with this, I get my G3 to be 2a plus 1 times x to the 2a divided by mu c squared x to the 2a. And of course, if now I realize that, of course, this is something that falls out, which is good. So I get as a result 2a plus 1 divided by mu c squared. That's now my G3. And again, here I can see this is independent or has become independent of x and y. So that means if my velocity profile is of this form, x to the 2a plus 1, then it turns out that G3 and G2, both of them become independent of x and y. And of course, that's exactly what I need to allow for a similarity solution. So if I just write down now this conclusion, so if I choose my free stream velocity UE of x to be some sort of constant times x to the 2a plus 1, or I can also call this now k of x to the power of n, if I want to now introduce yet another letter. So if I choose my free stream velocity to be a power law, so x to the n, then a self-similar solution does exist. And why does it exist? Well, because if I do it in this way, G2 and G3 are independent of x and y. So that means that that all my G1, G2, and G3s are only functions of eta, and I can go back to my, where the equation that I had in the beginning, then with the f's and G1 and G2 and G3, and I have an equation which is only in f and eta, so I can solve it, and then afterwards I can go backwards in my similarity transform, and calculate the profiles. So that's kind of the rationale of this. Okay? Now, guys, we have to wrap up a little bit the mess that we made with this exponent m, 2a plus 1, so the a, and then we also had the beta somewhere here. So we kind of need to fix that a little bit, because in the end they all mean the same thing. It's just in slightly different ways. So I have now introduced, and it's not me making this mess, by the way. I mean, people in the literature use a, m, and beta. So therefore, we just need to now make sure that we understand what is meant with all of that. So what I can see directly from here is that m is 2a plus 1. And then from Hartree, which we have written here, where we had beta h. Beta h was this 2a plus 1 divided by a plus 1. And of course, now you can directly also see that this can actually be written in terms of m, because you recognize here 2a plus 1 is kind of very similar to what m is. It actually turns out that this can be written as follows: 2m divided by m plus 1. So this would be how I would write the Hartree beta. And I guess with these two equations, this one and this one, you can now relate beta to m to a. Of course, the relevance with the a comes in because that is the exponent of the velocity. What do you have? No, the m here is the exponent of the velocity field, of the free stream velocity field, and a is the exponent that goes into the eta. So therefore, there is a relevance for all of them, but in the end, they really mean the same thing. Okay. So I guess the first test whether this actually all makes sense would be to check what Blasius, or how it looks like for Blasius. Well, in Blasius, our velocity profile is constant. So the free stream velocity is constant. So that means that m is actually 0. And if m is 0, that means that a, by virtue of this equation, is minus 1/2. And of course, that's exactly what we know, because that's what we have already written here. In the case of when we have a being 1/2, then we revert back to Blasius. But now we see that in this case, even it's consistent with the definition of m, because that means that we have no change in the free stream velocity. So in that sense, everything is good so far. Okay, what can we do now with this? Well, first of all, we can actually directly think of what happens to the boundary layer thickness if you have a pressure gradient pressure gradient laminar boundary layer. So how would we now calculate, or how would we now get an idea of what the scaling of the boundary layer thickness would be? Well, we can essentially go into this equation here, where we define our similarity variable, because that's the variable that tells us in what way would I scale my similarity solution when I go downstream as a function of x. So this a here, the exponent here, tells me how I would stretch the coordinate when I'm going downstream in x. So this exponent a is a measure of how the boundary layer would grow as a function of x. So that means, so what we're actually looking at for getting an idea of the boundary layer thickness is to look at lines where eta is constant as a function of downstream, because that would give us the stretching. And this eta is proportional, well, that's what I just said, that's proportional to the boundary layer thickness times x to the a. And of course, if I turn that around, that means that my boundary layer thickness would be proportional to x to the minus a. Right? That's the stretching that I would have downstream from my similarity variable. Now let's test that. For Blasius, we know that a is minus 1/2. This is what we said. And of course, that means that my delta would be proportional to x to the minus 1/2. So it would be proportional to x to the 1/2. So proportional to the square root of x. And that is exactly the scaling that we had earlier last time, I guess, when we had the square root growth of the boundary layer thickness. So that means for Blasius, everything is fine. But now, the cool thing is, we can now do that for Faulkner's scan. So we can now think of how would the acceleration or deceleration of the free stream actually affect our boundary layer growth. So what would you think? If I have an APG boundary layer, so if I reduce my velocity, would then the boundary layer grow faster or slower? If I have a decelerating boundary layer, do I have faster growth or lower growth? Decelerating boundary layer, think of the wing, where do I have the picture of the wing? That would be kind of in this region, so downstream towards the trailing edge, where we have an APG. How is the boundary layer growing there? Is it faster growing or slower than if it was a flat plate? Faster, yes, exactly. In the worst case, it would even separate. So that would mean it has grown very, very fast. Now, of course, the idea is, can we see that with our derivation? Because it would mean that for a specific m, if I have this m exponent here, I would then need to see that it would actually grow or decay in the proper way. Let's check this. So in Faulkner's scan, the a would be m minus 1 divided by 2. So that means my delta is now proportional to x to the 1 minus m divided by 2. And my free stream velocity, of course, is proportional to x to the n. Of course, now we see again, if m is 0, we get the Blasius again. That's of course very good. But now the question is, what would be a decelerating boundary layer? Would that be positive m or negative m? So if the free stream velocity is decelerating, it would be a slightly negative n, right? So that it goes down. What would that mean for delta? Well, it's a slightly negative m. I subtract m, so I add a little bit to this one here. And of course, that means the exponent is a little bit larger than 1/2. And of course, that's exactly what we expected. So if you have a decelerated boundary layer, you would expect an increase in boundary layer, increase in boundary layer thickness. So if I just write that down, if m is lower than 0, the flow is decelerating. That means that dp dx is larger than 0. Sorry, dp dx is larger than 0, and that would mean that we have an APG situation. And of course, the consequence, as we just said, that the boundary layer thickness is growing faster. And of course, that's exactly what you would expect. In the opposite case, when we have m being larger than 0, then we have the situation that the flow is accelerating. That means that dp dx is lower than 0, and this would be a favorable pressure gradient situation. And of course, then the consequence is that the boundary layer thickness is decreasing. Either decreasing, no, it's growing slower. It may also decrease, but it's growing slower. So that means that this n that we have introduced now can really be used as a measure for whether we have accelerating or decelerating boundary layers, because it's exactly the exponent that you would have in the free stream velocity. 0 means it's constant, positive means it's accelerating, negative means it's decelerating. So if I'm just making a few sketches with this, because I guess that's important to kind of remember. So if I have here in the middle the reference case where m is 0, and then my velocity profile probably would look like this, which is the normal Blasius profile. If I'm having on this side now the accelerated case, so that means now my boundary layer thickness is not as thick as the one that I have for Blasius. So that would mean probably something like this. Wait, something like this, I don't know. Where the gradient here is actually larger than it would be for the zero pressure gradient case. Of course, that's kind of also an interesting conclusion, that as soon as you have an accelerating boundary layer, you actually have a larger stress, larger skin friction at the wall. So that would now be, the FPG case. So this is ZPG for zero pressure gradient, and this would be FPG for favorable pressure. And of course, the same situation is then on the other side. When I have the APG, then I would have perhaps a situation like that, when the gradient is much lower. So this would be an APG case. And of course, maybe one thing that you can directly recognize, if I'm now increasing my adverse pressure gradient, so that means if I'm decreasing the m more and more, at some point I would actually decrease the gradient more and more up to the point that actually the gradient at the wall becomes 0. So that would then be the extreme case, at least in the consideration as we have right now. Then it would probably look something, initially at the extreme case, it would probably look something like this. But if I would decrease it even more, it may actually, if I show that here, so with the arrows, but it may actually be also that it would kind of go like this. So that you would actually at some point have, you would get separation. Because the deceleration is so strong that your flow would actually go backwards. And actually it turns out, we will see that later on, that the extreme case when you have 0 gradient here would correspond to an m which is approximately minus 0.09. And the purple case would be for a situation where the Faulkner scan solution is actually not valid anymore. You wouldn't be able to calculate the purple one using the tools that we have done right now. But up to the blue one, where you have a 0 gradient at the wall, this would be possible. Okay. So that kind of explains a little bit how you would now get in the effect of pressure gradient using different Falkner scan profiles with different acceleration parameters. Okay, any questions so far, or anything unclear?
In case if m increase more than 0,
yeah,
you mentioned that we have more scan fraction.
Yes.
But in Lausius case, if you increase the Reynolds number, you will decrease the scan fraction.
Yes.
So why is both of them different?
Well, I mean, of course, it's kind of. I guess it's a good question in the sense that what do I really mean with increase or decrease? I guess it's all about relative increases, because you're right. If the Reynolds number increases, you have generally a decrease of your skin friction, and that simply has to do with the fact that you have a growing boundary layer, so that locally, of course, if the boundary layer is growing, your gradient becomes less and less. But this has to do with the scaling of how, what you actually scale the skin friction with. So that means in any of these cases, if you increase the Reynolds number, you increase the thickness, so the gradient goes down. What I'm saying here is locally, if you keep the Reynolds number the same, you would just change the pressure gradient. The tendency is that if you have a thicker boundary or a thinner boundary layer, you would have a higher friction. But of course, if you then increase the Reynolds number again, then it would also go up again. Or the friction would go down, the thickness would go up. So it's all about the rate of how it would change. And of course, it's also kind of easy to understand, because in the limit of this one here, your skin friction locally is 0. So in the APG case, your friction is the tendency is that it decreases, which also makes sense. That's a problem of separation. You don't have enough momentum close to the wall. And of course, not having momentum close to the wall means that you don't have friction at all. So the typical ways of doing flow control to prevent separation is to energize the region close to the wall, to insert momentum. You can do many things. You can do suction. You can just, you can increase the speed at the wall, etc., or have vortices that kind of mix the flow. But it's kind of a general problem that APG means lower friction up to 0, and FPG means actually higher friction. Okay, let's do 2 examples for this, just to illustrate whether this is actually useful or not. I would like to show you 3 or 2.5 different cases where we can actually already now do some quite interesting conclusions. Let's do example number 1, and that is a flow case which is called the Hemans flow. Also, this goes back to a person that was studying that. Karl Hemans, he was also a graduate student of Ludwig Prandtl, also in Germany, 1885 to 1973. He was living, and he was looking at the following situation. You have a wall here, and you have a flow coming from this side, like this. And of course, what can this flow do? Well, in the middle here, it can go to what is called a stagnation point. And on these sides, it kind of has to kind of go over. So the Hemans flow is also called stagnation point flow. But if you now think of this actually looks very similar to this flow here, the wedge flow, with a specific beta. So now we can actually go in and think a little bit what actually all these derivations that we have done now actually means in terms of this case. Well, so compare to the wedge flow from above.
90 degree, right?
Sorry?
We'll take its symmetry and suppose theta is 90 degree.
Yeah, exactly. So pi times theta h from above is just pi here. So that means that for the He-man's flow, beta h is 1. So that's kind of the most extreme wedge if you wish. Now I guess you start to understand why this was chosen, or why Hartree was choosing the beta h in this way. So 1 is the stagnation point flow, essentially. Well, now of course, if you know that beta h is 1, we also know that this is 2m divided by m plus 1, as we derived before. And of course, that means then that m is 1 and a is 0. So we can calculate our, just by knowing beta h, we can calculate m and a based on the formulas that we had above. But now we can actually talk about the boundary layer thickness. With the boundary layer thickness, I mean, the sketch is maybe not extremely nice, but if I add a few more lines here, the boundary layer thickness kind of would be this thickness here. And then, of course, later on, this thickness. Sorry for the sketch. Sorry, something like this. So now the question is, if this is the x-coordinate, because in the sense of the wedge flow, this would be the coordinate along the wedge. What do you think? How is this boundary layer growing or decaying in the He-man's flow?
This is accelerating flow, right?
Maybe. Let's calculate it.
Is it faster?
Yes. Why?
Because if you substitute them in the x expression,
Exactly. Exactly. Now we just go into the formula for delta that we have calculated up here. We have delta being proportional to x to the 1 minus m divided by 2. So we have delta proportional to x to the 1 minus m divided by 2. And obviously, if I take m to be 1, I get, well, x to the 0, which means it's constant. So now we know that actually in the He-man's flow, the boundary layer thickness would essentially become constant. Of course, that's kind of an interesting phenomena, and we can now think also a little bit how this is really possible that it ends up like that. But in the end, this is the outcome of the scaling analysis that we have done so far. So the boundary layer thickness is constant.
Even at the stagnation point, or it doesn't require that?
Well, of course, that's a slight problem, of course, of the of this approximation. For the wedge flow, I mean, it's meant to be kind of in a region further away. So what do we have it? So I mean, from this inviscid flow, it's essentially the flow far away, I mean, some distance away from the actual coordinate. So it's really the kind of the scaling behavior if you look at these wedges. But of course, if you implement that and if you simulate that or do an experiment, you can see that behavior. So you can go in, you can measure your boundary layer thickness, and you can see how it changes. Now to your question, now of course the question is also, is it an accelerating flow or not? Where do we have it? Here. We can also look at UE. UE is proportional to x to the n. So that means x to the n. I mean, this for n being 1, this just becomes x. So that means, of course, this increases with linearly with the distance from the point in the middle. So that, of course, also means locally the boundary layer thickness is, of course, then measured with respect to the local UE. So that means that the profile as the velocity inside is, of course, scaled with this x. It's just the thickness that is constant. Not that the profile is constant. It's the thickness that is constant. Okay, so this was one example. The second example that I would like to show you is also one of those kind of, how should I say, famous or important example, because actually it happens something which is also slightly counterintuitive. It's the example of a so-called sink flow. So how does a sink flow look like? Sink flow looks like this, that we have a situation that is like that. And to make things more interesting, now in this case the flow is in this direction. So we have two plates that are straight, and they just decrease as a function of x. So sink flow, of course, means that at some point they will all converge to 0. So that's the idea. But kind of in the same spirit as we said before, that we're maybe only considering this region here. Also here, we're kind of considering this region. We're excluding kind of the part where everything converges into 1. Okay. Now, let's try to think how we could treat this flow using the analysis that we have done so far. So first of all, let's introduce a coordinate, and I take again an x coordinate like this, starting here at the point of convergence, going into the domain. Then, of course, one thing we directly can write down from mass conservation. We know that if I call this height, if this height is h of x, then I know that h of x times ue of x needs to be constant. Oh, that's just mass conservation. I mean, the thinner it becomes, the higher the velocity needs to be. Otherwise, I will lose mass, and that's not. For my scaling behavior, or because I'm only interested in scaling, I can just say it's 1, but it wouldn't matter. But of course, that means at the end of the day that I can say that my ue of x would be 1 over h of x, and vice versa. Now in this case, I have h being x. Right, that's my linear increase of the thickness. So that means my ue of x is just 1 over x. Again, I'm removing all scalings. It's really just the idea of I mean, all the prefactors are removed. It's just the principal dependence on x that is relevant. And of course, this is x to the minus 1. Okay. Now I have all I need, actually. Because this minus 1 here, this would correspond to the m. So that means in this case, I would have m being 1, minus 1, yes. I hope I have it here as well. Yes. Okay. This is m is minus 1. And of course, with this, I can go to my formula that I have used before. So that means my delta is proportional to x to the 1 minus n divided by 2. And of course, in this case, if I have 1 minus minus 1 gives 2 divided by 2 gives 1. So actually delta is proportional to x. So that means if I'm now thinking of this flow here, that my boundary layer thickness is kind of decreasing in the same way as the thickness of this channel is decreasing. And of course, this is actually, and at first you may think, yeah, well, it's clear, it has to be like that. But it's actually not so clear, because at the same time as you go in, your free stream velocity, so your UE is actually increasing. But yet, everything is just scaling in perfectly the same way from this position to this position to this position. So you have an increase linearly of your velocity, 1 over x increase, and at the same time the boundary layer thickness increases as x, or decreases as x. So that means in this case, and the sink flow is actually the only flow where you have something that we could call complete similarity, because everything just scales properly. So this would be a flow that is in complete equilibrium, because there's nothing that scales in an anomalous way. Okay. So this was my last example for the sink flow, or for the Falcon-Scan boundary layers. There's just one little part that I would like to add for the Falcon-Scan boundary layers, because so far we now have only looked at the boundary layer thickness. We have only looked how the scaling of the boundary layer thickness looks like, the m's, the betas, the a's. But there's actually one thing we have not discussed, and that is actually the profiles, or how the Falcon-Scan boundary layer equations would actually look like. We just talked about, so we just identified, okay, there is a similarity solution possible, and then based on the coefficients that we got for this similarity solution, we could get out all of these scalings. But actually, we should also talk about the actual solution. And that's the last thing. So let's go back now. So let's go back to the Falcon-Scan boundary layer profile. If you remember, we said that this eta, so this, the similarity variable, is this c times y times x to the a. So that was the first thing that we actually that we mentioned. So that was the whole approach of Falcon-Scan, to say that the variation of x can be encoded in a free exponent, rather than just a being minus 1/2. What needs to be done here, or what we need to understand here, is actually this coefficient c, which we have not talked about. We just said, well, it's a constant times y times x to the a. But if you remember, in Blasius, we actually had a value for that c. It was the square root of u infinity divided by the viscosity. But here we just said it's c. So somehow we need to find a way of determining this c, and then based on that we can then really calculate what is g1, g2, and g3, and we can come up with the equations, or the ordinary differential equation that we actually can solve for getting the Falcon-Scan profile. But I guess now it's 5 o'clock, so doing this we will do after the break, and I guess that will maybe take 10 minutes or 10-15 minutes, and Afterwards, we will close everything about boundary layers and come to a much more fun topic, maybe, and that would be stability, or transition and stability. So 15 minutes more with Falconer's Can, and then we go to stability. Okay? So let's take a break, and we continue at 1:15.